Okay, transformer fans, first transformer video, I showed you the math according to K8byp. I've made 6 transformers. They don't work. Why? I've tested the math. I've tested the windings. I know I got good cores, got good wire. I measured inductances. I tested the formulas. The formulas work. The transformer doesn't work. Why? Because while I got a reasonable pass band, the resistive value on input was like 25 or 30 ohms and it's supposed to be 50. And according to K8byp, the fix for that is to increase the number of both windings. So I filled the core up and got 70 ohms on the input, which is overshoot. So great, I can unwind the windings. I did a frequency sweep, and here the pass band's up about 30 megahertz. And it turns out I was using the wrong cores. The 67 material is for 10 megahertz and above, and I'm trying to use it at 2 or 3. So got new cores coming from our friends at Newark. In the meantime, transformer theory, and real transformer theory, not the grossly oversimplified nonsense about turns ratio, but this is the scientific theory based on differential equations. The first thing to go through is to put aside this nonsense about reactance being ohms. Ohms are R. Resistance, ohms, is the international unit of electrical resistance. Reactance is not ohms. This mistake came in the computer era because computers cannot understand phase diagrams. Down below you see a graph of a impedance with R along the horizontal line and a rotation in degree angle which represents inductive reactance. You'll see in my network videos I tell you R plus or minus X, some quantity, not in ohms. X is phase. For a single signal with reactance, the phase is the difference in time between a peak of the voltage and a peak in the current. That's not ohms. The graph down below, the 4-quadrant XY graph, quadrant 1, upper right, counterclockwise 2, 3, 4. The left side's imaginary, the right side's real. Plus top is inductive. Down below in quadrant 4, in 3 and 4 is negative capacitive reactance. This is vital to understanding why transformer theory is wrong and how to fix it. And the reason we can't make transformers that work is because we got the wrong theories. So having done that, let's move on. What is a transformer? A transformer follows network theory, like a pi or T network, 3 elements. I've gone over those in great detail here. Transformers and networks create 2 resistive images. Impedances are not allowed. No reactance is allowed, which shoots the first principle of the transformer being inductive in and capacitive out and making 0 phase, shoots that right down. That's wrong. The purpose of a transformer is to transform resistive characteristics from input to output. The characteristic of the input is the output load resistance transformed through the transformer and presenting an image that appears resistive because the phase angle is 0. Reactance is phase angle, it's not ohms. The output image is the resistance of the RF generator propagated through a transform that appears as pardon the term, an imaginary resistive value on the output with 0 phase angle. But we got to explain how we get a 0 phase angle in and 0 phase angle out from 2 inductors, because the classical model of a transformer being 3 inductors is wrong. Just look at it at DC, you'll see it's wrong. The classical model, and you'll see this in Radio Engineer's Handbook by Terman, an otherwise good book, is that the primary is inductive, and to get a secondary that is 0 phase, it must be capacitance because the primary is plus 90 and the secondary is minus 90, and that is wrong. Prove it's wrong. Well, the coupling in a transformer is magnetic, not electrical, so therefore the secondary is not capacitive. An inductive function transferring to a capacitive is a resonant function, not broadbanded, and a transformer is broadband. I proved that to you in the first video. 3. The theory of L is plus 90 and C is minus 90 equals 0 is wrong. Plus 90 and plus 90 is also 0. Look at our sine wave down here. The two zero phase points are at 0 degrees in the sine wave and 180 degrees. In between, on the top hump or bottom hump, is rotating through the phase angle in sine, or cosine if you're starting at a maximum. But this proves that this model of secondary capacitance is grossly wrong. And if we don't get past that, we can't see how a transformer works. Now, it's critical to understand there are two phase concepts. There's phase shift with regard to a single signal. Take an RF generator, 50 ohms out, put into a R50 and X50 circuit. There'll be a significant phase shift because according to Eli Ice, voltage leads in an inductor, current leads in a capacitor. The current will lead because there's reactance, and that's a shift between the phase of the voltage and phase of the current. But what we're looking at here is phase delay, and that's a propagation delay. And here's where we think of this error with understanding antennas and transmission lines as circuits when they aren't. That's in the time domain. Phase shift is in circuits. Phase delay is a propagation concept. And in between the primary inductor and secondary inductor in a transformer is a magnetic field, and that is not a circuit. Like antennas with electrical and magnetic fields are not circuits and cannot be analyzed by circuit analysis. The transformer model as 3 inductors is wrong, and that's in a radio engineer's handbook. God bless Terman. Look at it. There's a symbol for the transformer on the left. 2 coils separated by 2 solid lines. The lines solid indicate an iron core. Dashed lines in between, 3 dashes on each line, is air core. Not equal to 3 inductors, because the 3 inductors are DC short, and there are not 3 windings in a transformer. What the T network of inductors with the vertical inductor in the center really should imply is a magnetic coupling, because we can't have connection between the 2 inductors on top, because transformer is not a DC bypass. The critical concept with the vertical inductor in the T network is that represents something called the coefficient of coupling K. That K value is between 0 and 1. Back in the old days in the 1940s with link-coupled transformer outputs to air core transformers, the small winding secondary is movable and rotatable. Those had a coefficient of something like 0.25 or 0.28. Very poor coupling. The point of a toroid core is to get the windings together in the same space with a high permeability and raise that coefficient upwards of 0.8 or 0.9. Much more efficiency. The gross error in transformer theory is that it only focuses on the turns ratio, and that's wrong. I proved in the first video that a transformer designed like this is loosely coupled with the windings, primary and secondary, displaced on opposite sides of the core. And although it was a 1-to-2 ratio of turns, the voltage secondary and primary were equal to 1. The turns ratio with the windings separated did not work. When the secondary winding with more turns was stretched across the core, so the ends of the primary and secondary windings were essentially touching, then the ratio went from 1 to 1.45 in voltage. So the transformer began to work when the windings ends were almost touching. But when they're separated, the transformer failed. It did transform the R value, though. Now we've got a serious problem. We've got no theories to go with. So let's fix that. The transformer is 2 inductors. With a K of 0, there are 2 independent inductors in space. They're not sharing any field, so the secondary is dead. The fundamental differential equation for an inductor is V equals L di over dt, and di dt represents or is representing the sine or cosine wave. We just call it sine. What's missing here is this reversible arrow that indicates a transform from the circuit world on the left, V equals L di dt, to the magnetic field state. And this is what's left out in electrical engineering for a large part. This is conservation of energy. The current, as a result of voltage through the inductor, results in a magnetic field. and that magnetic field reverses and returns to the current state, if you will. To make a transformer, we double the differential equation, with the m, which is represented by or representing the variable k, the coefficient of coupling, assuming that's 1. Then on the primary side on the left, we have V, which is a generator source, equals L, the primary inductance, dIdt, which is the rate of current change. That induces a magnetic moment. Moment means instant. That instantly, with no delay, couples into the same equation on the secondary, and I've written it backwards to kind of show the process from the left to the right. The magnetic field is instantly coupled into the secondary winding with no time delay in theory. That becomes dIdt L equals voltage of the secondary. If we consider 180 degrees actually being 0 degrees, then A and B are equal. And that equation, although it looks a little funny, is correct because it obeys conservation of energy. Now, if we take this at 90 degrees when the inductors are charged, dIdt becomes 0, becomes the top of the sine steady state. Where that goes is that we integrate that and we get the inductor energy equation. Inductors do not have power. What's a power in an inductor? 0, because the phase angle is 90. And think of the term power factor. When the power factor in electrical power is 90, there's no work done. Work is only done when the phase angle is 0. That becomes a familiar W equals Li squared over 2. W on the left implies circuit power, and these are circuit variables on the right. But when that's in a magnetic state, there's no power, it's magnetic energy. In an inductor, L is the primary charging, holds a magnetic field till I begins to reduce in a circuit. That's after the sine peak. Then that system reverses and the magnetic field drives current back through the primary coil, the primary winding. The transformer is a primary charges to an M field through the coefficient of coupling of 1, so no losses to the secondary. That becomes the secondary output voltage instantaneously. Both of these halves happen at the same time and the phase is effectively 0. Now, resistive transform. A network transforms two R values by two resistive images that are created by two reactances. And if you'll follow Kiekert's math down below here, you'll see the strange fact that violates electrical physics, that these two inductors, which are purely reactive, look and act like resistance. From Kiekert's book, RF Circuits, Chapter 3, I mentioned this book in my first transformer video. The occurrence ratio is the square root of the secondary inductance divided by primary inductance, and the square root of that. Also, the center frequency of the transformer's response is the low frequency times high frequency square root of that. And the incorrectly called impedance, no impedance in a transformer. There's no phase. What that really means is the reactance, the center reactance of the magnetizing inductance and the loss inductance is a product of the two and the square root. And at the same time, the center resistive characteristic value in the middle of the passband is equal to the square root of the low resistance at the lower cutoff and the high resistive characteristic at the upper cutoff, which means the action of the L sub M and L sub S at the 3 dB down frequencies on above and below the frequency response. So what that means is that the square root of actually, it's not ZLZH, it's XLXH equals the square root of RLRH. Therefore, reactance impedance equals resistance. That can't be, it violates the laws of physics, but yet it is, and the math proves it. And here's the magic of a transformer that takes reactance and makes it look like a resistance. The characteristic resistive value of the transformer and its passband is also the square root of the generator resistance times the load resistance. This seems to completely contradict all of electrical physics and network theory, but it doesn't, and I'm going to explain why. Like I'd shown you previously, transformer magic is X of primary mapping through the coefficient of coupling, the K. That's the magnetic field coupling between the primary and secondary completely with no loss. That transforms to the reactance of the secondary. The primary on the left couples magnetic field. From those two vertical lines, it's a mirror image going to the right, so it's the same thing as an inductor charging and then discharging, although this happens at the same time without the 90-degree shift. So with the same differential on both sides and complete coupling in the middle, we get what is a resistive image. That gives us the windings, inductance, reactance, gives us over to looking at the ratio. Turns ratio, number of secondary divided by number of primary, is normally stated to be the ratio of the voltage on a secondary over the voltage of the primary, but I just showed you in the first video that's wrong, because when the windings are uncoupled, that secondary ratio is not the turns ratio, it's 1 to 1. Now when I stretch these secondary turns till they touch the primary, that Vs over Vp, the secondary voltage over the primary voltage, went to about 1.45. What that proves is that the coefficient of coupling, K, was increased. So effectively, the turns ratio equals Vs over Vp times the K. Now that may not be quite mathematically correct, but it's functionally correct. No coupling, no transformer action, no V sub S. So what's wrong with the toroid core? Is it broken? See the mechanical diagram? The primary winding on the left, 1 ratio. The secondary separated on the right, 2 ratio, with the K being real low. Ns over Mp equals Rs over Rp, not equal to Vs over Vp, and that just throws transformer theory out the window. In this case, Vs over Vp equaled 1. 1 volt peak to peak on the input through a 1 to 2 transformer was 1 volt peak to peak on the output. Why was there no coupling? Well, toroid theory is that the toroid conserves all the magnetic field so it doesn't go off into space, so therefore it's all coupled to the secondary. Wrong! And I proved it. Is the energy lost in the core by dissipation? Well, that's easy to find because the dissipation losses are stated for the core materials and they're on the minus 10 to the 6th order. But wind a primary winding into a resonant circuit test and see with a resistor, a 50 ohm resistor, you'll find essentially no losses. When I did that with a generator of about 0.835 volts, I got on the order of millivolts of losses. So the core is not dissipating the energy. And here at a couple volts peak to peak drive, we're not going to feel any heat in a core like these. The theory for you to test is whether it's cancellation. Inductors have a polarity like a capacitor. The inductor is like a permanent magnet. It has a south and a north. If you've ever tested a coil with a permanent magnet, you'll find that. The inductor on this toroid core in the drawing is south on the top and north on the bottom. And at the far opposite side of the core, do south and north cancel? Plus and minus do. So in theory, maybe if the secondary winding is on the far other side, there's a flux reduction or cancellation. It's trying to induce opposite polarities in the same winding, and the result is 0. You test that by throwing a couple turns around the opposite side of the core and then moving those turns and see what you get. What you'll find is as you move the turns closer around the empty core to the primary, the coupling goes up and the coupled energy goes up. From conservation, the beauty of a magnetic core is that it conserves the field lines that normally wrap around an air core inductor like that. The lines go through the turns, out the end, back around the outside, and back in. It conserves those two not going off into free space. the flux in between the turns of the inductor is conserved to magnetic loops, a circular path. In the toroid, that is incidental with the amount of the core that the winding is around. So that flux is concentrated in the core, coincident with the inductive winding, and it's taking that field that would be going off in other directions and putting it into the core. But it's going to stay in that space pretty much between the physical winding and the core and not wrap all the way around the core. That's indicated by winding that 1 to 2 on opposite sides and then stretching the windings till the ends met. We can't get a transformer that works unless we understand the physical meaning of K, the coefficient. K is mutual coupling. K is unitless from 0 to 1, it's relative. K equals 1 means that all the magnetic flux of the primary couples into the secondary. The problem is, in these windings, there are 3 parts that are not shown in a typical schematic diagram. There's 3 parts to this coupling. There's the core coupled through the mu of the core, which is represented by or representing the A sub L value. Then, why bifilar windings are popular, but limited to only 1 to 1, 1 to 2, 1 to 3, is B, coupling from the primary to the secondary, not through the core but through the air. You take a bifilar winding, one wire is a primary, one's a secondary, they're wound exactly together, there's coupling directly between the wires. The problem there is that if the turns ratio is not identical over the whole length of both windings, then that air coupled from primary to secondary will not be the correct ratio. And that's a real problem to fix. Then there's flux that is wasted, which is what K8byp says is L sub S, which is what is really called uncoupled flux. And K8byp calls L sub S the leakage flux. Leakage tends to be a capacitor term. But that's flux that goes spewing off into space that isn't coupled by the processes of A through the core or B from primary to secondary or vice versa. That's kind of a loss. What I measured by coupling or decoupling the windings by moving them closer together or further apart is that the L sub S is greatly reduced when the 2 windings are coincident, when they're wound on top of each other, right on the same core, right in between each other. L sub S goes down. When the windings are decoupled, separated, the L sub S goes up, but the coupling is lost. And if you follow the formula for the characteristic resistive value, which is the square root of the characteristic resistive at the low and high frequencies, which is related to the L sub M and the L sub S, the square root of those, is it increasing either the primary inductance and by the turns ratio of the secondary, or increasing the L sub S will both raise the resistive characteristic, and that's what my transformers were lacking. They were only 25 or 30 ohms. They needed to be 50. So I could decouple the windings and move the primary physically away and raise L sub S. L sub M would be the same, and the R value would go up, but the transformer wouldn't have the correct turns ratio then. So according to K8byp, the way to do that is calculate the R sub C, the characteristic of the transformer, what it is, and what it should be, and find the multiplier as to how many turns to add to the primary and the secondary. And raising both the primary and secondary inductance raises both L sub M and L sub S and brings the resistive characteristic up without loss of coupling. And that's what I did by taking the 67 core and filling it completely full of windings and getting a 70 ohm. And that would have worked, except the passband was way off. So we maximize A and B, the core coupled, and B, the flux from the primary to secondary between the windings, by coincidental windings. It's best if it's a bifilar winding, but that is higher capacitance because the closer the primary and secondary windings are together, the greatly more capacitance there is, and that leads to resonance. C, the uncoupled flux tends to be on the OD of the wires outside the core, and that is aggravated by bending the wire around the core, because the bend in the wire is a flux concentration. Since the turns ratio is proportional to the square root of the L sub m and the L sub s values of Kiekert's book, L sub s can be increased, but that causes loss of coupling, so K goes down and we shoot ourselves in the foot. Now, to affect the exact transformer ratio, the exact inductive ratios, because turns ratio in the end doesn't mean much. That's just mechanical. And I was able to get a precise inductive ratio of about 2.25, 2.3, which in theory, that contradicts toroid theory, which says we can only get even number or single integer number of terms. We can get in between that by stretching or compressing the turns. That allows more coupling primary to secondary, but that concentrates the flux in a smaller volume of the core, and the core doesn't dissipate heat very well. It's partly ceramic. So when the windings are compressed to increase the inductance and to help the primary and secondary span the same physical length, if the flux is concentrated in part of the core, that means that part of the core is going to get hotter, and the core is not real great at dissipating heat. So here is a correct model, a complete model of either the primary or secondary windings. And this is representing the windings themselves and their couplings. The top is the iron core with the two straight lines on the right. That's through the turns ratio. In series with that is the coupling between the wires themselves within the correct turns ratio through air with the dashed lines. Then down below, if you see the two L sub s values, and notice they're perpendicular to each other. And that perpendicular means there's no coupling between them, but they are air core inductances. See the single set of three dashed lines. But the coupling path between the two is X'd out. And that's what happens when magnetic fields are at right angles. They don't couple. So there's no primary to secondary coupling between the two. So the bottom two that aren't coupled are the L sub s, and the top two are through the core, and the air coupling, where the air is through the proper turns ratio, that's the L sub m. And you won't find that in the books, but that is how it works. And there's a roll of the appropriate paper with which you can dispose of ordinary transformer theory, because that's all it's worth. So next video, I'll get the proper cores and I'll wind it, and I'll predict that it's a core problem, and I'll predict that the next transformer will work. So there is real transformer theory from K8byp and only here.